edition of the VLab Forum, and this is your host, Steve Smith, Director of the VLab, and I'm here with John Mecikalski, who is our Technical Production Manager, managing the GoToMeeting, and so today we have a talk by, make sure I get this right, John Mecikalski, is that right?
Yeah, that's correct, Mecikalski, yeah.
Okay, from University of Alabama and in Huntsville, co-authors, I don't know if they'll be speaking or not, Chris Jewett and Jason Apke. And we're going to hear about the GOES-R, is that Convective Initiation Product Suite? Is that correct? The
That's
CI.
correct, yeah.
Yes. So format of these, of course, to remind everyone, is John will do about 30 minutes or so of content, and then we will have question and answer. If you're on the GoToMeeting, we ask that you use the chat feature of the GoToMeeting to ask a question, or the raise your hand feature, so that we can unmute you at the appropriate time and let you ask your question directly to John. Also a reminder that these sessions are recorded, and the recording will be uploaded to the VLab Forum website immediately after the conclusion of the talk, so that you can share that with your colleagues at your leisure. So without further ado, John, you may proceed.
Okay. Yeah. So I think if this is my first time doing one of these, so I hope we get the content down. It's the appropriate content. So what I was going to talk about today is the GOES-R Convective Initiation Product Suite, and I call it a product suite because we started out with one project, the Convective Initiation product, which basically has been demonstrated at the Experimental Warning Program, EWP, HWT, and the Aviation Weather Test Bed as well. And so we're actually migrating to some newer products, and I was going to actually show those. Okay, so there we go. So so the basic overview of this is, like I said, I'll give an update, a very brief update on the 0 to 1 hour convective initiation methodology, mainly because it's been around for so long. I think we've kind of hit a plateau with the algorithm with the current GOES, in my mind. There's not a lot more we can really do to improve it, and we're desperately waiting GOES-R. Some of the new stuff we've done, which is what I'm going to spend more time on, we've tailored a version of the the CI product to be more of a severe indicator of severe storms. We have an early CI that is in demonstration right now that takes advantage of the 1-minute super rapid scan. I'll talk a little bit about something that's really new. It's this 1 to 4 hour probabilistic convective initiation methodology, and then using mesoscale atmospheric motion vectors on the 1-minute data to delineate storm types. That's something that's probably going to be operational next year or late this year. And then just some data simulation results. So this next slide, number 3, is the basic flow chart for the convective initiation. Please stop me if I'm going too fast, or, if people want to ask a question. This is, like I said, something that's been around for about a decade now, or even a little bit more, where we take the convective clouds and the GOES imagery, which are identified just as the convective cloud. So it's a very nice cloud mask we developed. We actually track the clouds as they grow, and what it does is gives this very nice lead time to new storm development, so way ahead of radar. This lower right-hand figure is something. It's an older version. It was the yes/no version, kind of deterministic, and we validate as convective initiation using a radar-based definition of the first 35 dBz radar echo at the -10 degrees C altitude, and we use MRMS data, the mosaic, to actually validate that. So that's a legacy convective initiation definition that extends back into the 1960s. I'm showing this slide, number 4, to kind of exemplify where we are today. This is the result of a 2015 study where we evaluated logistic regression in random forest, 2 machine learning approaches, and we have accuracies about 85 to 87%. There's a lot more details of the accuracy determination in that science paper that came out last year. The methodology actually also detects convective initiation at night. As you'll see in a minute, we are detecting convective initiation beneath thin cirrus, so we're using cloud property data sets to actually help our algorithm perform better where forecasters need help determining convective initiation. A lot of our earlier comments at HWT were for, if you know reasonable amounts of satellite interpretation, you can pretty much interpret what a cumulus cloud looks like in an image, and you're going to not need a lot of help. But at night and under thin cirrus, that's where it gets to be tricky. So that's what we've actually done some separate science studies on that. The other big thing we did in the last 3 or 4 years is to make this not a satellite-only problem. So it's logistic regression, so you actually need a big training database of, in this case, we have 120,000 plus CI events across the whole country, and it's automated, so we can both collect, monitor, and validate our convective initiation all at the same time using the MRMS radar. And what we also do is bring in a lot of environmental data from the RAP model. So our predictor set is not just satellite observations. And I want to make this clear because some prior versions, it was all satellite. Not that we were doing terrible, but we actually got a very large step function improvement in accuracy once we included the background information from the RAP model. So we use a 1-hour forecast from the RAP to get CAPE, convective inhibition, and you see the variables there on the right. So that gives our forecast the high accuracy that we're getting, and we're going to continue this methodology as we move into GOES-R. As we move into GOES-R world, late this year, we're going to update the satellite interest fields to, right now we're using rather poor indicators of cloud top glaciation, but we're going to have something like the 8.7 channel that's going to, or 8.5 channel that's going to very much help us do a better job, and the higher resolution visible and the higher resolution infrared we're going to take advantage of as well. This is the GOES East domain picture. I think this is, the next slide showing the product, which is just a very clean looking product. We display it on top of visible imagery during the day or infrared at night. And each cumulus cloud then gets a probability that it's going to make rain in the next 45 minutes to an hour. We operate on rapid scan and normal 15-minute data. The big thing here is that a lot of forecasters looked at this, and that's great. It's actually situational awareness, where you can see where the atmosphere is generally unstable. If there's ongoing rain, we might make a nowcast under the cirrus, but we pretty much figure forecasters are going to be looking at radar. And but anyway, so what we've done now is to trend towards more of a focused product that gets to some of the regional hazards. We've actually done this again. We've actually trained the algorithm as well to identify the first lightning flash, and that's I'm not mentioning that here because that's still under evaluation. Like I said, this is a day-night algorithm, slide number 7. We use cloud properties from the University of Wisconsin SIMS that we receive every 15 minutes as well to basically help us improve nighttime detection of cumulus clouds and also, like I said, convective initiation below cirrus. This is just an example of kind of the original way we were doing the nighttime detection, which had a lot of false alarms, and then the new way. And now with the 4 kilometer GOES, as you might imagine, the product does not work as well at night. It's hard to get a small cumulus cloud that's 4 kilometers in size, so oftentimes if you're not filling an entire pixel, it's not going to show up as a very good identification of a cumulus cloud, or we're going to get a lower lead time because the clouds are just bigger when we first see them, but I'm expecting a big improvement with GOES-R. That's just the validating radar. This slide number 8 kind of is a quick example of some of the uses, some of the regional uses. So in Albuquerque, we have had a lot of feedback on this product because they use it where there's radar blockage, and otherwise they wouldn't have any information. So forecast offices are able to draw this into AWIPs and display it alongside of other products. Yeah, so there's a slide I don't have in here, but there's actually been some offices that have combined these products with a WRF-based forecast. So if they're running WRF locally, they can have kind of a convective initiation threat region that they can actually show then. And again, this is something that's been around for quite a while. So I'm limiting my discussion about the CI product itself, just because it's yeah. So if anybody has any questions about availability or access, let me know. The kind of the interesting thing when you're in the hazardous weather testbed world is the main focus is on severe storms, hence the name. So aviation weather people are really interested in maybe all kinds of convective initiation because it's a hazard to everything from big airplanes landing at big airports to general aviation. So, but anyways, from the HWT, we kind of got some very good feedback in 2013 on how the product was one of the first satellite-based products that people would look at to try to get a sense for what's going on, like what's the storm of the day or the supercell of the day. And so what you'll see circled here is the GOES-R CI. In this particular case, showed a really good hit on the Moore, Oklahoma tornado in 2013. This is from a paper by Gravel et al. 2015 that came out in BAMS. It just got published. And it gave a really good indication on the first storms. You see them circled there, the first clouds that were growing rapidly along the dry line. That later became the storms that produced the tornado itself. So this led us down the path of trying to use logistic regression with these background indicators to predict, could we actually give a lead time for which cloud was going to become the supercell. And so you'll see an example. So this next slide, number 11, is just a follow-on. The interesting thing here is if you do go from the cumulus cloud stage to the supercell, and we obviously realize there's a lot of evolution that occurs in the cloud during those two things, but if you can give forecasters that heads up to that first big supercell, they're getting it's almost this worn-on forecast framework where you're getting a very early lead time. It's focusing attention on that storm, and you're getting a really, really long lead time, maybe over an hour, in some cases maybe an hour and a half to the storm of the afternoon or one of them. This next slide number, I think it's slide number 12, this is from last week. So this is May 9th, where we actually have two versions of the product now running at the hazardous weather testbed that just ended. One in the upper left is the CI product, and I have circled the cloud that has a 98% chance of making rain or convective initiation. And then the severe CI, I also have that same cloud circled. The severe CI product alone pegged that with a 67% chance of becoming a severe storm. Well, if you actually run this through in time, and I actually think I probably have some of these arrows pointed in the wrong place, but in any event, what it amounts to, no, they're not. What it amounts to is that in 1945, we gave this heads up to that particular cloud. By 22 UTC, there was a tornado produced where those two lines basically converged. So we're effectively gave a really long lead time to this particular case, and the event continued, so we were getting additional hits. And the very nice thing is that you'll see that there are clouds. We really only were focused, the severe CI product only really picks out the clouds that have the greatest likelihood of becoming severe storms. So This slide number 13, which is somewhat animated, and I'm hoping the internet keeps up with this, but this is the same storm on May 9th, and we have the regular CI product on the left, the severe CI product on the right, and what you'll see is the, again, we're actually getting a very good hit from the severe CI product, and what we started to do, which is kind of interesting, is putting little polygons downstream of where we kind of expect the cloud to grow. You'll see the radar looping in the lower left, and really what this comes down to is not that we want to put out a warning. The polygons are not designed to be a warning, but it's more or less a threat region, so people can downstream anticipate where that particular cloud is going to grow and evolve into something of an organized storm. Kind of changing gears, slide number 14. This is another example of the convective initiation product where we take the 1-minute data from super rapid scan. We simplify the algorithm because we don't need to track the clouds so much, but what we do is we're evaluating the cumulus clouds relative to the temperature, the level of free convection. So you can actually do a delta there and figure out, well, how much colder are the clouds compared to the level of free convection, and it's really a early indication of just atmospheric destabilization. So the colder than LFC region is circled in a green area, the warmer than is circled in a red. Roughly speaking, I mean, this is just with the forecasters, they could actually look at this in real time. We're going to be demonstrating this by the end of this summer in a real-time fashion with GOES 14. So going in a different direction again, so one of the things that we were challenged to do with the study is, so the 0 to 1 hour convective initiation product, again, it's really focused on current cumulus clouds as they grow and evolve. And what we wanted to do, actually what I really have been wanting to do since I moved to this part of the country, is trying to get a sense for what's going to happen, say, 1, 2, 3, 4 hours into the future. Because this, to me, when it comes to a forecast of convective storm development, every single day down here in the summer can have this 30 to 40% chance of rain, and it becomes really, you don't really know, are you going to get rained on or are you not? So we took the same machine learning approach to the 0 to 1 hour and applied it to, again, the 1 hour, 2 hour, 3 hour, and 4 hour into the future. So I'm showing this slide. It's a lot of detail, and there's a science paper that's under development. But we initially started off with 750 predictors. So we take into account things like model forecasts of storms, the instability as it evolves over the 2 to 3 hour or 4 hour time frame. Is it getting more or less unstable? We look at the cloud mask out of the convective initiation algorithm. We actually evaluate how much that's changing over time. So what you really can do is, in a region, say 20 kilometers square, you can collect all these predictor variables and effectively produce a gridded product of probabilities. So we started out with 750 predictors. We used an information gain algorithm to reduce that predictor set to 234, and then we actually ended up using random forest, which is a machine learning approach to get to a field importance, and we ended up with 59 input variables. So what we would do is, say every 13 or 5 kilometers, we would collect all this information, and you're taking delta T's, so you're taking trends over this, say, 2 to 3 or 4 hour period. What we did find on the next slide, number 16, we used the Weka package, which I'm sure if anybody's familiar with it, it's a way of taking a very large training database and using many, maybe up to 20 different machine learning approaches, and it'll tell you which machine learning approach works the best. So it was a very powerful tool, the bottom line is the random forest, those red numbers gave us the best answers. So basically the same algorithm we're using for the 0 to 1 hour is the methodology we used for the, say, the 2 to 3 or 4 hour convective initiation. Slide number 17. This is the end result of all the work. So I skipped a lot of details. And so this is what the product would look like. This is just on a given day. This is the 24th of July, 2014 in the afternoon. And what we did here is we have 2-hour CI predictions, then 1 hour. And on the next slide, you're going to see 0 hour. But what we're doing now is attempting to run this in real time and also validating this. But the validation statistics show that we're basically in the 60 to 75% correct range, depending on how far out we go. And I think the goal I had for this was to provide forecasters with not a static 30 to 40% chance of rain, but you're basically taking things like topography and winds, blowing up and down the topography, land cover information, stability information from a model, forecast information from a model, and then real-time cloud information and trends in all of that to try to say, well, this is probably what the atmosphere wants to do. So it's destabilizing in rather small regions, so we can assign probabilities of convective initiation from 50 to 80% based on that. So this is 2 hours on the left, 1 hour on the right. And then if you go to 0 hours on the next slide, number 18, you'll just see, generally speaking, what we're noticing is that 3 or 4 hours into the future, you'll see, say, 55 to 60% probabilities. And as you get closer to the current time, those regions remain coherent and their probabilities tend to increase. So this was the result of a lot of work that ended this spring, and so now we're like I said, we're in the process of making this run in real time and just doing a more elaborate validation of this before we really give it to a lot of other users. But I wanted to show this because it's just very new work. And then the last thing I'll talk about, this is a slide, the next slide, just seeing an animated. Does the animation work pretty well?
Yeah, we can see it, John.
Okay, so this is, so I have a student, Jason Apke, who we wanted to take advantage of this 1 minute data pretty much as we possibly can. One of them is the early convective initiation product, but the other thing that we noticed is this is a very mature supercell storm, and so we noticed, this is based on just visual appearance, that the cloud top appears to be rotating. So what we wanted to do is take our atmospheric motion vector algorithm, which we run all the time, and see what we could actually learn of supercell storms. And so this is the animation of the cloud. And so the main motivation for this particular part of the talk is to again derive these atmospheric motion vectors using the 1 minute data. We analyzed cases of supercells and then ordinary convective storms to try to see, can we actually differentiate storm types using these wind data sets? So, and then given that satellite offers this very nice piece of information to the larger puzzle of severe storms forecasting, what other information could we be providing the forecasters? And so we started off with a rather simple Barnes objective analysis to analyze divergence and vorticity over the top of the storm. So this is a really interesting component of this work as well. So typically atmospheric motion vectors are used on 15-minute data to get geostrophically balanced flows and height assigned flows that actually go into models. So they assimilate those data sets into models. What we wanted to do is run this for a convective storm. So if you look at the typical rapid scan 7-minute, you're not getting a lot of vectors that mean much. So this was a sense for, well, the reason nobody's done this already is because the current data set's just too much evolves in 7 minutes to allow these tracking procedures to work. If you do 1 minute, you'll see you derive these very nice coherent flows at anvil level. In the anvil, we know changes altitudes, but this is an anvil top or cloud top anvil level. And then the nice thing is you can actually derive something like divergence. So what we see here are these really nice coherent patterns of divergence. And I'm going to show some loops. I think I have about, I have several more slides left on this same subject, and then my talk will be over. But what we're seeing is you can actually watch the divergence increase and decrease as a function of time. We've noticed things that when the divergence is very strong, it seems to correlate very nicely to the cycling of the supercell. When the divergence starts to weaken, it isn't uncommon to see large hail reports within the next 15 minutes. So it seems like as the updraft weakens, what the updrafts are lofting the large hail and forming the large hail, and once they weaken, then the large hail tends to fall out. And the other thing we can derive is vorticity, and so we've actually learned some really interesting things. This is an animation then of these divergence as a function of time. And you'll see, you know, the divergence increases and decreases, and it seems to be very strongly coupled to a region of overshooting tops, which is in fact the main mesocyclone on this particular day. The next slide is vorticity, and it shows an extremely nice vorticity couplet. So when we first saw this, we didn't know if this was an artifact of our analysis. Could have been obstacle flow around the storm, or could have just been something related to slower winds in the environment. And again, objective analysis procedures can really cause a signature that's not real. So we took a really good look into this. The next slide is just this animation. So we're getting very consistent vorticity on these vorticity couplets. In this particular case, it was a very well-defined supercell storm in Colorado. This next very pretty slide is just what the storm looked like from underneath. So there was no doubt that this was an extremely deep mesocyclone. So it was a very good storm to begin with in terms of our analysis. And then the next slide is just an animation of radar confirming that this was in fact a very well-defined mesocyclone. So that was really, you know, very good to know. The next thing we did, this is an ordinary convective storm over North Alabama. This is divergence. The divergence associated with ordinary storms is really about 5 times lower. And so that turned into be a signature we would maybe have expected. It just implies that very organized storms are cycling much more mass than ordinary storms. But from a forecaster standpoint, they could actually maybe use this information to delineate storm types. So if you have a relatively low amount of divergence, that would more or less imply a pulse-like storm. And then if we look at vorticity from the ordinary convection, we really don't even see any organized couplets. So that was kind of a nice thing to see, that the couplets of vorticity more or less were real signatures. And then this is just that same supercell I showed before on kind of a busier map where the green dots are the hail reports. And again, we've done some initial analysis to correlate the strong divergence with large hail, and there seems to be some predictive lead time there, but we got a little bit more work to do. Yeah, so this is vorticity, again, with the same hail reports. I'm going to kind of skip through that. The one thing we really have done, and then I'm going to finish off with a few slides here, is just to speed the process up. We've actually taken a look at WRF simulations of, you know, what does a high-resolution model of the same storm generally look like? Are we really seeing real features? So the first thing I'm going to show is this recursive filter. So we got away from the barn scheme. This runs extremely fast, like in 20 seconds, so we can now keep up with the 1 minute or 30-second data. we just get very nice consistent flows. This is divergence again, and this is vorticity, or divergence for these storms. Recursive objective analysis so we're kind of comparing, yeah, this is divergence for these two, for this particular case. And then vorticity, this is the, you know, we're seeing very nice fields coming from this much quicker recursive filter approach. Then lastly, we're working with the Esrael people, NOAA Esrael, to try to assimilate these observations into models. This slide number 34 is kind of busy. It shows this diabatic digital filter initialization, which is what we're testing in with the HER model. So the idea is you could take your cloud top growth information, turn it into a heating rate, and that effectively would be information that would improve 2 to 6 hour forecast of storms. And this is just basically this is the RAP and the HER model framework that we've been using. We've been working with Steve Wegant at Esrael. This is an initial test, slide number 36, on the with and without assimilation. So there was some early indications when we started doing this that you're seeing an improvement in your convective storm forecast, especially using the clouds to tell you where to put the heating into the model. And then this other slide, number 35, is it's kind of a busy slide. It shows a control. The SOS in the middle is our strength of signal, or our GOES-R CI indicators of new storms. And what you're seeing, the fact that the blue line is above the black line is a very good indication that at least from hour 16 to 20, we're seeing an improvement in the, I think that's the CSI score. So we're actually seeing an improvement in our, oh no, this is DBZ times 100. Actually, I don't know what that upper thing is, but bottom line is we're seeing an improvement in the HER model forecast just in terms of precipitation. And the CRM4 is a cloud resolving model that's more like a baseline test that's more explicit. So, anyways, it looks like there's a path forward to take the HER model, to take these convective initiation fields and routinely assimilate them into the HER model. And then my last slide, number 38, is just an overview, which is the same as my outline. I just want to kind of more or less to repeat that we are working on a suite of products based on the CI algorithm, going in a number of different directions, and we more or less hope to keep doing this work for the next several years as we transition into GOES-R. So with that, I'll take any questions.
Okay, thanks, John. Very good. Lots of content there, and I'm sure we've got questions. So first, remind everyone, if you're on the go to use the raise your hand feature if you'd like to ask a question, and John Chattel will unmute you, or the chat. If you choose, you can also chat in a question. So do we have anyone? I guess we got the first question there from Kenneth James. Can you discuss, I'm reading this, of course, can you discuss the false alarm rate for basic and severe CI from 0 to 6 hours, false alarm rate? Basically, what, yeah, how are you, what kind of false alarm rates are you dealing with?
Well, yeah, that's a good question. From the 0 to 1 hour CI, the 2015 paper that it goes over that pretty extensively. Our false alarm rates are about 22 to 25%, if I can remember those numbers correctly, in the 0 to 1 hour time frame, and that's using the latest version. So one thing we did suffer from with prior versions when we used satellite only is we ended up with pretty significant false alarms, maybe like 40 or 45 or even 50%. So we've really knocked those false alarms down to the low to mid 20s. Now the 1 to 4 hour convective initiation, I don't know. I mean, that's something we're evaluating. We did a really big we assess the term accuracy or the skill score accuracy. I really want to say that our false alarms are a big function of the probability for the 1 to 4 hour, and not to make this a really long answer, but that's definitely what we noticed in the 0 to 1 hour convective initiation is our best accuracy. Our lowest false alarms are seen when we have probabilities assigned to the clouds of about 70%, 60 to 70%. So if you can imagine, if we get the cloud that's in this mid-range of rapid growth and our algorithm assigns about a 65% or 75% chance that it's going to actually make a new storm, then our false alarm rates are very, very small. And if the algorithms assign a low probability, then our false alarms will generally be higher. So, and I think that makes a little bit sense. So.
Okay. Questions in the room? Go ahead, Dave.
Yeah, this is Dave Kitzmiller. Can you tell us where products like this run when they're in operations? Is it within NESDIS?
Well,
somewhere?
Yeah. Actually, they run in our building here. We haven't made the transition to running them in NESDIS, and that's I'm not sure why. We actually started on the path with a PSBI effort, and that didn't really go anywhere. And then we actually revisited that a year ago, and that also didn't go anywhere. And so right now they're running in my lab here, and it's all supported by NOAA funds, so that's very good. So there's a little bit of a weak link there. I think the goal is once we get to the GOES-R world, we'll update our algorithms, and then they would get transitioned to NESDIS.
Okay.
And I do have to give a quick pat on the back to NASA SPORT, the Short-Term Prediction and Research Transition Center. They've actually been very, very helpful to provide a pathway to operations. So we've been using them quite heavily. So we'll run them on our machines, but then they grab the files and get them into AWIPS as fast as possible.
Okay, thanks. John, this is Steve Smith. I got a question. In terms of the object base, the 0 to 1 hour, you got to define the object, right, initially.
Yes.
So what exceeds the threshold to say this is a cloud? I guess you go by a cloud top temperature or something?
Yeah, that's a good question. So we developed our own convective cloud mask. So it's a cloud mask that identifies something like 150 or 160 different types of clouds just using those. And what we did, it was an unsupervised learning method, but what we did is in that method, there's about 9 different kinds of cumulus clouds. So we have fair weather cumulus, towering cumulus, cumulus with small anvils, and so forth. What we do is we use those clusters of cumulus cloud types to make objects. So we wrote our own software package that actually does its best to cluster and find coherent anything from even 1 pixel size objects to sometimes you get these, I don't want to say blobs, but these shapes of clouds, especially if they're very linear features. So once we have those objects defined in a grid, then we can apply our logistic regression algorithm using the pixels within each object. And we typically take the coldest 25% of the object's pixels to delineate the active updraft area. So at the end of the day, they are basically a cloud algorithm identified cumulus cloud that becomes the kind of the seed for an object. And other people have used like the WIDS2. It's like a watershed approach using, say, cloud top temperature or something, and we haven't done that. We really have stuck to this this more sophisticated, in my mind, more sophisticated approach to identifying cloud types.
Okay, so once you identify the cloud, then do you use some kind of motion vector to predict where it'll be in an hour?
Yes. So that's the atmospheric motion vector component I showed with respect to cloud types. We run that at the same time, and we found that tracking cumulus clouds, say in 15 minutes, we have to do these trend analyses every 15 minutes as the clouds grow. And using model-based winds was not a good approach, so we derived cloud motions from the clouds themselves, and that allows us to effectively isolate where the prior object was that was smaller, and then the current time object, which ideally would be larger. And you can do the delta, then you can do your channel differences or your trends of cloud top cooling or whatever on that. And then we use that same motion to project forward in time. So that's, technically we could have a polygon for every single cumulus cloud. The maps would get terribly busy, so we haven't done that. But that would be the idea.
Okay. And last one from me for the moment. So what's your ground truth for this particular product? How do you verify your forecast?
Yeah. So for the convective initiation products, we use the MRMS. That's the radar mosaic produced by NSSL. They have a very nice product. It's the reflectivity at the -10 degrees sea level, and we use that to basically verify convective initiation. So we used to use rainfall at the ground, but our lowest level reflectivity, we have used that in the past, but we've kind of stuck now to this reflectivity at the -10 degrees sea level.
Okay, thanks. So we got a question in the room. Go ahead, Bob.
Okay, this is Bob Vaughn. A number of questions. I'll only ask one or two, I guess. In a very time-sensitive product like this, now you indicated in one remark it was getting on AWIPS. How soon can you get these out? In other words, how timely is the product when it actually arrives at a WFO, for instance?
Yeah, so we've got our algorithm. So if we get data, we get our satellite data from NESDIS. So that comes ideally within seconds of the image being downloaded. The algorithm itself runs in 1 minute and 40 seconds on average, or about 2 minutes or less. So really our latency in-house is very low. It could be like 3.5 minutes. The big problem comes in then once we transfer the file via LDM from us to the NASA Sport, and then they send it somewhere. We unfortunately add another 5 to maybe 7 minutes of latency. So that is, like I said, that's a really weak link in this whole process, and I would think that in the future we would absolutely get away from this need to transmit the product through 2 or 3 different people to get it to a WFO. So I'm going to say the WFO latency might be more like 12 minutes, and it's not because the product isn't done early enough. We admittedly have worked extremely hard to get it to run as fast as possible in-house, and I do think this argues to transition this algorithm kind of off our platforms and into more of a NOAA platform.
Yeah, that seems pretty critical. One more question. One of the products you showed was around the Alabama region, I believe. Now this is sort of a generalized thing so that you have an algorithm that works on any grid point within a certain area and so forth. And is that algorithm applicable over the whole country or what?
Well, yeah, so the 0 to 1 hour algorithm runs over the entire CONUS from 25 degrees north to about 50 degrees north. And we actually have a version running in Central America on 15-minute data. the 0 to the 1, I should say the 1 to 4 hour prediction, which I'm showing this image now over Alabama, that's a limited product for now. It's so new. We worked on it over last year, and we're going to be running that in real time over the southeast United States later this summer. So the bottom line is the CI product, 0 to 1 hour, is available pretty much to everyone in the whole country, every 15 minutes. And this 1 to 4 hour one, which I show over limited domain, isn't quite available yet.
Thank you.
We've gotten a few questions on the chat. I'll sort of relay these through. One, I believe, is from Arlene Lang. How does the product compare with the Auto Nowcaster? Is the question. Are you familiar with the Auto Nowcaster, John?
Yes, I am. I have not worked directly with the Auto Nowcaster, so I am not. I don't want to misspeak. I am aware that the Auto Nowcaster usually is set up at a radar site, so it needs some sort of a centrally located radar. It also does take into account, it actually integrates radar. I believe it integrates model, forecast information, and satellite. Now, I do believe it also requires a fair amount of site-specific tuning, and I'm not really I know in Huntsville here it actually runs at the Redstone Arsenal, which is basically right outside my window, but I can't say where else it runs. I know they've done testing with it. So our algorithm, being that it's machine learning and it focuses on integrating model fields and satellite fields, it's probably quite a lot simpler than the Auto Nowcaster. We do not integrate radar or radar fine lines or anything into the problem. But I know their algorithm runs on like a fuzzy logic approach too. So there's some similarities, and I think ours is a little bit more general because as long as we have a geostationary satellite view and access to the data, we can just run over very large regions. We don't need radar. So. Okay,
well, for those of you who really want to, get more about Auto Nowcaster, I'll just put this in. Next month on June 15th, we have talk by John Crockett about the Auto Nowcaster, and I know from inside information that it's running CONUS now and is going to be implemented or is being implemented as part of MRMS. So John, if you want to tune in for that talk as well to get more information, you're certainly welcome to do that. We'll send you the invite to that.
Yeah, that would be good. Yeah, please do.
Sure. So I've got a question also from Ting T. Very interesting in the logistic regression. The response and the predictors are localized, or are the response and the predictors, are they localized, or are there long distance impacts?
Well, to the extent that I understand the question, all the predictors we use, the predictors are very, very cloud specific. So every object or every cloud object has a set of predictors, and we then take RAP model sounding data that's from non-precipitating grid points in the RAP model. So the goal is to take very local predictors around every single cloud, and that's how we get this 0 to 1 hour. Now in the 1 to 4 hour, the idea is that we do take some forecast information from the RAP model, so we're trying to anticipate a little bit into the future, as well as some trend information of the current cloud information. So it's a combination of localized predictors and maybe non-local predictors.
Okay. I think Ting says thanks. So you answered her question, or his question.
Yeah, a lot of some of the predictors in the 1 to 4 hour don't change from time to time. There are things like slope and topography and land cover type. We take things like soil moisture and soil temperature that might only change once or twice a day. So those are local predictors, but they're more static.
Okay. Very good. I got a follow-up question as well. So when you do verification for this, do you do any spatial or temporal sort of smoothing to provide, I presume what's the natural scale, horizontal spatial scale you're using, a kilometer, 4 kilometers?
Yeah, roughly it's the scale of the satellite, which is, well, this is a 1 kilometer product, but admittedly it's based on 4 kilometer infrared. The validation is the MRMS resolution, which I think is a kilometer. And again, we look downstream from wherever we have an object because we know the motion, so we would look downstream in that next 45 minutes to an hour. There is really no smoothing. I mean, we try not to smooth the product or smooth the to my knowledge, we don't do any smoothing in this whole thing.
Well, I guess to speak more clearly, do you do any when you're doing the verification? Do you relax the criteria? I mean, do you have to be how close? Do you have to be right on the grid point to get a hit, or can you be, 10 kilometers away, 20 kilometers away? And same thing on the time. Do you have to be within 5 minutes, 10 minutes, 30 minutes to get a hit?
Well, because it's the 0 to 1 hour prediction, what we do is if we have a probability of convective initiation for a cloud and it's moving, let's say it's moving to the east at, 10 miles an hour or 20 miles an hour, we would go downstream 1 hour and make a circle. So some reasonable amount of a circle. So I think we take the size of the object and I think we multiply that by 3 or 4. So the idea there is if you have a cumulus cloud and it would grow in size horizontally and it would move downstream, it would produce rain. The one thing we struggle with in highly sheared environments is that the storm motion is challenging. The cloud may move in one direction, the storm's going to move in another. So there's a little bit of we do. The criteria really is 1 hour and then some function of the size of the initial object. So obviously if we made that ridiculously large, we'd probably get ridiculous validation statistics. So when we did work on the validation, there was a lot of concern that we weren't going to oversell the product. So we picked reasonable constraints to validate it.
Okay.
In other words, you are tracking an object, and this is what you are trying to compare with the radar at the valid time, right?
Did you get that, John? The question.
I got some of it, yeah.
Yeah. So you're doing the verification on an object, not on a grid.
Yes. Okay. Exactly. We're doing it on an object basis.
This is Glenn again. It seems like to me products like this are very useful for forecasters to look at and so forth, maybe without even talking much about verification or validation. But if you get to really verifying and saying how correct you are and stuff like that, it seems like to me that really doesn't make much sense unless you compare it to something else. I mean, you might you quote a certain hit factor, let's say 50%. Well, you might ask, and that's over some sort of a circle and some sort of a time period. You might also ask, well, what would persistence give you over that same circle, and so on. In other words, how much better are you than something else when you get right down to verification?
No, that's a really good point. I think I'm going to have to think about that. I think.
Let me follow up just a bit. this is what you see in papers all the time. You see a new technique and you see a verification, but it's not compared with anything really in operation. So a person that's going to implement something really doesn't have any idea whether to implement it or not if you don't have comparison with what is currently available. So I just encourage you to think about that kind of thing if you're going to verify at all.
Okay. Now I can say that the only thing I can say there is that this is because of the 0 to 1 hour is more or less a linear extrapolation. We are probably giving a probability that the cumulus cloud is going to continue to grow and make rain. And not all of them do that. So when we say we're 85% accurate, I think what we're saying is that given for the tests we apply to a given cumulus cloud, if it just keeps growing, 85% of the time it's going to make rain. I see what you're saying is that there needs to be some basis. Now the 1 to 4 hour, that I think might be a little different because it is challenging to know. The comparison we were making there was to say a RAP model forecast. So if the forecasters had a HER forecast or a RAP model forecast, are we able to effectively do better than that? And that's I think that gets along the lines of what you were saying is, what's a 3-hour forecast for rainfall from the HER, and what do we show here? So
exactly.
So that's going to be within the paper that's forthcoming, at least for the 1 to 4 hour. Now the 0 to 1 hour, that's a little. I guess we would then need to do a similar prediction against the model or similar comparison.
Okay, thanks, John. I got one more. You may have. Okay, we got 2 more. A quick one. I think you touched on this, but how do you deal when you got a CONUS-wide product that's based off satellite, critically dependent on satellite algorithms, and you have cirrus obscuration? How do you then default to some other algorithm which is mainly based on radar, or what do you do there?
Well, we actually did a study in which if you used visible optical depth, which again that's more of a daytime product, of course, you can actually get enough information through thin enough cirrus. And I did a study using cloud properties, the GOES-R cloud properties using visible optical depth, and a couple other cloud properties themselves. And you do see pretty large increases in values of some of these optical depth parameters, regardless of whether there's cirrus there or not. And so that gave us a very good handle on using the cloud properties where we have, so from our cloud mask, we identify cirrus as well. So typically in the early versions, we were just masking out all the cirrus because we really couldn't deal with it. From the, once we have a cirrus cloud type, then we actually use a cloud property field to identify objects in cloud optical depth and perform our analysis on that. It's a lower resolution product because it's infrared based, but it gives us a lot of information where we don't have cirrus, and we still again don't use radar. So. Okay, thanks. We got one more question.
Well, actually, I have a couple of questions. In the 1 to 4 hour forecast, do you find a falling off in how well your technique works, like out towards the 3 or 4 hour period? In other words, is there like a logical time period for which your technique has some value?
Yeah, that's a good question. So ideally, our 0 to 1 hour methodology, which differs from our 1 to 4 hour, we should get the same answer at 1 hour. And I think what we do is we get, say, the 85% chance at 1 hour from the 0 to 1 hour. From the 1 to 4 hour methodology, we're sitting at something like a 75 to 77% accuracy at 1 hour. And by 2 hours, it falls by about 7 or 8%. In 3 hours, it falls again. In 4 hours, it falls again. So we're seeing this relatively reasonable fall off in our accuracies as we go forward in time. The idea there is that by 4 hours, the HER model would probably fill in and start picking up and becoming the main forecast guidance that people would use. So I didn't really want to extend the product beyond 4 hours, but it just becomes really hard that, you know, the atmosphere does destabilize over periods of time, but things become a little less consistent out the 3 or 4 hours. But we are seeing that.
Okay, and do you ever see the opposite, like you're honing in on some areas where you think there'll be convective initiation or growth. Do you ever find convective storms develop where you didn't anticipate them?
You know, if there isn't a cumulus cloud, then, you know, then the question is, well, how would that ever happen? At night, I do think we miss a fair amount, because if you get either a misclassification of a cloud, then we would certainly have a miss. And we do apply a CAPE mask, so if there's a case where we would accidentally mask out a region where the RAP model says there's no instability, and in nature there actually is, we probably do get misses in those cases too.
And so finally, go ahead, sorry.
No, that's all I was going to say.
And finally, do you have a definitive plan for fielding, for implementation?
You mean implementation in the Weather Service?
Yeah.
Yeah, I mean, right now, I mean, there's a fair amount of transition activities going on. The algorithm has been streamlined, and I guess once we would get a green light, it could actually be transitioned to NOAA, and, you know, or however they want to run that. So, you know, that answer is yes. It just hasn't seemed to quite, we haven't quite gotten there yet.
So nothing is scheduled at the time being?
No, it was scheduled last spring, and then that kind of stopped. So I'm not sure where that's going. I think they may be waiting for GOES-R itself.
Okay, well, we're going to have to cut it off now because we're a little bit past the top of the hour. I want to thank John again for a really interesting talk, and remind everyone that this recording will be uploaded to the VLab Forum website shortly after. So if you didn't get to see it all, or you want to share it, you can do that once it's there. And again, coming up on June 15th, we have a talk on the Auto Nowcaster, very similar topic, and with different methodologies about short-term nowcasting of thunderstorms. July 20th talk is on Wave Run-Up Project by Anthony Mignoni and Rich Okulski. And then coming up in August, just-in-time training plug-in project, Jason Burks. So thanks, everyone, and we will see you in June.